So this is the outline I'm going to follow. I will quickly recall what are ultra-cooled neutrons, and then I will just go to particle physics, and in particular to the measurement of the neutron lifetime. I will focus on the two techniques used to measure the neutron lifetime, which are the beam method and the container method. And then I'll go to the so-called neutron lifetime anomaly, and I'll close with the conclusions. So I will just want to start briefly recalling what are the physical features of ultra-cooled neutrons by doing a parallel with the electromagnetic radiation, which might help to have an intuitive understanding of what are ultra-cooled neutrons. So this is part of the electromagnetic spectrum. And now if we just delete everything we don't need, what we know already is that the equivalent of thermal neutrons in terms of wavelength are X-rays, because they both have the wavelength corresponding to atomic distances in matter. So that's why they're good for diffraction. Now, when we cool down the neutrons, their energy decreases and the wavelength extends. And with ultra-cold neutron, we can reach a wavelength of around 100, 500 nanometers, which is exactly the wavelength of visible light. When we talk about visible light, we know that it's always in terms of collective phenomena, such as reflection or refraction, since the wavelength is so long that can't distinguish different scatterers, but matter acts as a uniform medium. This is exactly what happens with ultra-cooled neutrons. Their wavelength is so long that the single atoms can't be distinguished really. So we will talk about reflection, refraction, and microscopic phenomena such as inelastic scattering by a single atom or capture will be possible, but quite rare. So what could we do with this kind of neutrons? The main application is in particle physics. Here I showed a table with the 4 fundamental interactions. And you can see in the second column, where is the strength, that this is the coupling constant of every interaction. For the fourth, it can vary a lot, starting from the strong interaction, which is strong, to gravity, which is totally weak compared to the strong. So it means that if we want to measure the fundamental parameters of the weakest interactions, it's difficult when the 4 of them are acting, because the weakest will be overwhelmed by the strongest. So this is why a free ultra-cold neutron could be useful. First of all, because being free, there is no gluon exchange, which are the carriers of the strong interaction. So without gluon exchange, there is no strong interaction. Secondly, the neutron is neutral. So it's almost non-sensitive to the electromagnetic interactions, and which is good because many experiments of this kind would be impossible with charged particles, because the Coulomb force would overwhelm other forces by many orders of magnitude. Therefore, we will be studying the parameters of the weak interaction. Also, the neutron is quite convenient because it has this parameter, which is called branching ratio, which is equal to 1. The branching ratio is the probability that a certain particle will decay into a precise decay mode compared to the whole range of possibility of decay modes for that particle. So it means that the neutron, as far as we know, decays 100% of the times in proton, electron, and neutrino. And this is experimentally really good, because it means that it gives you the best statistics. Otherwise, there are also other decays that could be studied, but experimentally, the experiment is limited by this really small branching ratio. So as I said, when it's free, the neutron decays. Particle physicists would say that at the heart of this decay, there is a weak charge current weak interaction, which enables the down quark to transform into an up quark by the exchange of a double boson, which later decays in electron and antineutrino. The interest in measuring the neutron lifetime, it's mainly in two fields. The first one is the Big Bang theory, which can predict the abundances of, for example, deuterium or helium-3 or 4 at the very beginning of the early universe. For example, they predict that at the initial stage of the universe, there were neutrons and protons exchanging, converting into each other, and then at the so-called freeze-out, the expansion of the universe accelerated compared to the exchange rate between the two, and nearly all neutrons quickly end up bounding into nuclei. So the neutron lifetime can help to determine the primordial helium abundance. The second field is quantum field theory. The neutron lifetime can be a means for testing the unitarity of the CKM matrix. This is the matrix that rotates the flavor eigenstates or the mass eigenstates into the weak eigenstates. Understanding the meaning of this matrix here is not really important, but what is interesting is that for particle physicists, it's important to verify that this matrix is unitary, because it means that if it's unitary, our understanding of the quark generation is complete, and there are no quarks which are missing. Otherwise, if there is a deviation through unitarity, it means that there is still something that we didn't understand, and there's a particle that has to be discovered. So, but what's the link with the neutron lifetime? The first element of the matrix is related to the probability of transition between down and up quark, which is exactly what happens when the neutron decays. And it's also the biggest value of the first line. So the uncertainty on the unitarity is linked directly to the uncertainty on the neutron lifetime. So I just named two fields where measuring the lifetime of the neutron could be interesting. Now let's see how this can be done. The first method is called the beam method, which corresponds to observe the decay products of the beta decay of the neutron during a certain period of time and passing through an experimental apparatus. So in practice, there is a well-collimated beam of neutrons that passes through a decay volume, which is a proton trap composed of several electrodes. The first three segments are called the door, and they are held at 800 volts. Then there is a variable number of electrodes which are at ground, and they are the trap itself. And then the mirror, which are three segments also at 800 volts. So if a neutron decays while it's in the trap, the proton will be confined by both the magnetic field and the door and the mirror, because at high potential. And after a certain period of time, what happens is that the upstream electrodes are lowered to ground. And there is also a little ramp voltage, which is applied to accelerate the protons to the detector. So what is measured is the number of protons after a certain number of time, after a certain time. The second method is the container method or bottle method, which consists of confining a certain number of ultra-cold neutrons into a bottle and then count the remaining ones after some period. Then the procedure is repeated a few times, and the decay, the lifetime is extracted from a fit of the storage curve. As I wrote here, the storage time is not directly related to the neutron lifetime because there are also some effects which has to be taken into account that cause the loss of some neutrons, which are mainly the interaction with the wall of the bottle. But we'll see that later a bit more. And so there are several kinds of bottles. There are material bottles, which rely on the fact that substances which have a positive scattering length will cause repulsive pseudo-potential for the ultra-cold neutrons. There are also gravitational bottles, which rely on the fact that the strength of the gravitational interaction between ultra-cold neutrons and the gravitational field is comparable to the effective Fermi potential for most materials. So this means that there are traps which can be built with open tops because there will be gravity which will confine them vertically. And this is also useful to spill out all the more energetic neutrons that we don't want inside the trap. And also the bottles can be done with the magnetic fields. So an inhomogeneous magnetic field of a few Tesla can confine this neutron, these ultra-cold neutrons, and which will act as a repulsive field for the neutrons. And this is a summary. So the beam method measures the decay products and in specific the protons, while the bottle method just counts as a function of time how many neutrons are remaining. So do the two methods agree? The answer is no. Here I put a summary of all the measurements of the lifetime of the neutron. And solid circles indicate the beam method, and open squares indicate bottle measurements. There are also these gray points, which means that the measurement has been withdrawn or just replaced by later work. And the discrepancy of the results is quite significant. It's about 8 seconds, which corresponds to almost 4 sigma. And it is called the neutron lifetime anomaly. The reason of this significant discrepancy is not really clear. And there are mainly two approaches to try to explain it. The first approach is the appealing solution, which is looking for deviations from the standard model. So there is a group of physicists that say that instead of having a branching ratio of 1 for the decay neutron, proton, electron, antineutrino, instead the branching ratio is about 0.99, and there is another decay channel which is exotic and involves a dark matter particle. And this 1% branching ratio would explain the discrepancy of 8 seconds. And the reason why it would explain it is that the beam method measures only the decays that produce protons, while the bottle method, in the opposite, would measure every decay channel. And this is one of the hypothetical solution. Second one is the boring solution, which is that trying to provide analysis of an additional systematic error which was overlooked. So if we go more in detail with it, as I said, the beam method measures the products, while the container measures the neutrons. So for the beam method, the problem is with, for example, backscattering from the detector surface. But the biggest source of error, according to some articles, is that there is a probability of proton losses due to charge exchange collisions with residual gas molecules, which were stored in the trap. And for example, for oxides, molecules like oxide of carbon or water molecules, it's possible there are some remaining molecules that scatter with the protons and there is a charge exchange. For the container method, for example, for wall bottles, for material bottles, one problem is with that the total reflection can be fully achieved because of inelastic upscattering or absorption. And for example, if a neutron has an inelastic scattering event with the wall, there is a possibility that he will be heated and it will quickly escape the trap, but it will be measured as a neutron that decayed. And for that problem is mostly because of the wall material, which is responsible for it. For example, most of materials exposed to the atmosphere develop a layer of hydrogen, which significantly increases the probability of cold neutrons loss. And another problem would be due to quasi-trapped neutrons, which are neutrons whose energy would be higher than the potential, but which are anyway trapped because they're on a stable trajectory because of the geometry of the trap. And it's believed that the problem of the container can be solved with magnetic bottles, for example, or varying the geometric configuration of the trap or the energy range of the neutrons. So scientists believe that the container method is more reliable. So summarizing what's the problem, the two methods measure two different observables, which are opposite. This means that a leak in the beam method would cause to overestimate the number of remaining neutrons, while a leak in the container method would underestimate it. And this error will be transferred to the estimation of the lifetime. The question is whether the two procedures can arrive at a common conclusion. And what I saw is that many believe that the beam method is less reliable, while the container method could be measuring more precisely the true lifetime of the neutron. So in conclusion, I would say that the most popular opinion now is that the bottle measurements are closer to the real lifetime, and that a dark branching region is excluded. But also that many groups are trying to improve the measurements, both with magnetic bottles and also improving the beam method. For example, measuring instead of protons, the electrons, which is not easier, but it's in principle a different experiment from counting the protons. And that's it. The anomaly is not fully understood yet. And that's it. Thank you for your attention. And I would like to thank Tobias Jenke for the reference.